You want intense. You want experiments that break reality at its seams. You want quantum physics pushed to limits that sound impossible. The 7 experiments you're about to hear operate at temperatures colder than deep space, probe particles that Einstein himself refused to believe in, and manipulate matter in ways that violate every instinct you trust. These aren't theoretical games. These are real machines running right now. Scientists at Google, Harvard, Columbia, and labs across 3 continents are building devices that challenge the foundation of what's possible. Some operate near absolute zero. Others use magnets strong enough to destroy your credit cards from across a room. One experiment hunts a particle so elusive it was declared impossible to detect. Another teleports information through the same cables carrying your Netflix stream. This is happening. In your lifetime, 7 experiments. Each one changes what we thought was law. If you value documented quantum physics and cutting-edge science history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from Physical Review letters published October 20 to 25, tracking the newest time crystal research at Vienna University of Technology, and Nature Communications. August 2024, detailing the graviton detection framework from Stevens Institute of Technology. Sources that show we're diving deep past the surface noise into primary experimental data. Now back to the information. Number 1, graviton detection. The particle that might not exist. 2024, Stevens Institute of Technology, New Jersey. For 90 years, physicists talked about gravitons like ghosts. The quantum building blocks of gravity. Particles so weak, so impossibly small, that detecting one would require a detector the size of Jupiter parked next to a neutron star. Freeman Dyson calculated the math in 2003. His conclusion crushed hope. You'd wait longer than the age of the universe to catch a single graviton. Game over, except Igor Pavlovsky didn't accept game over. August 2024. His team at Stevens published a paper in Nature Communications that broke the consensus. They found a way. Not with a Jupiter-sized machine, with a heavy metal cylinder cooled to near absolute zero and fitted with quantum sensors, a Weber bar, old technology from the 1960s, reborn with quantum precision. The trick sits in quantum sensing and gravitational wave data. When LIGO detected gravitational waves from colliding neutron stars in 2017, it recorded a tsunami of gravitons flooding Earth, trillions upon trillions. But LIGO can't catch individuals. It's built for the wave, not the particle. Pavlovsky's setup changes that. Take a beryllium or aluminum cylinder weighing up to a ton. Cool it to its quantum ground state, the lowest possible energy. Then wait for a gravitational wave from a black hole collision to pass through. The wave carries gravitons. If one graviton hits the cylinder, it causes a discrete quantum jump, a single step up in energy. You measure that jump. You've detected a graviton, one single indivisible unit of gravity. The resonator must vibrate when absorbing a graviton from an incoming gravitational wave. That vibration changes the quantum state of the cylinder. The change is detectable. It's analogous to the photoelectric effect Einstein used to prove light comes in particles called photons. Same principle. Gravitational waves interact with matter in discrete steps. Energy exchanges in single units. Gravitons absorbed or emitted one at a time. The experiment couples existing detection technology, the acoustic resonator, with next-generation energy state detection. Quantum sensing tracks how the cylinder's energy changes in a single step. That step is the graviton signature. Pavlovsky's postdoctoral researcher Srinath Manikandan explained the process. First, cool the material, then monitor how energy changes in a single step. This is achievable through quantum sensing. Graduate student Germain Tobar added context. By observing quantum jumps in the material, we deduce that a graviton was absorbed. The jumps are small but distinct. The cylinder resonates with gravitational waves at specific frequencies. When a wave loaded with gravity particles encounters the prepared bar, it causes a jump up a quantum energy step. The single jump corresponds to absorption of only one graviton, something thought impossible to detect previously. The challenge is keeping the sensor bar in a very low energy state, then monitoring its change to another extremely low but slightly higher energy state. The experimental setup must operate with exquisite sensitivity. One of the coldest systems ever studied. Even tiny energy dissipations are measurable through temperature changes recorded using quantum thermometry. The team's calculations show the measurements could be done using devices similar to Weber bars. Thick, heavy cylindrical bars up to a ton, named for inventor Joseph Weber. These bars fell into disuse as optical-based detection technologies emerged, but for graviton hunting, they work. The experiment doesn't yet exist in full form. The necessary sensing technology is still developing. Quantum jumps have been observed in materials recently, but not yet at the masses required. But technology advances rapidly. Stevens physics professor Igor Pikovsky stated his confidence: the experiment should work to confirm predictions of quantum gravity according to calculations. The group's technical demonstration in the paper set the physics world on fire. March under 20 to 25 hours. Nature Communications announced the paper ranked as the most downloaded physics article of 2024, accessed approximately 34,000 times worldwide. 25% more than the journal's next most popular physics paper. The revolutionary paper proposes a theoretical method for capturing graviton absorption events using quantum sensing technologies now within reach of science. A supercooled detector bar of beryllium or similar metal interacting with periodic gravitational waves that occur after large neutron star collisions in space. When waves encounter the bars, they resonate, causing small, distinct jumps. Each jump resolves to absorption of a single graviton. Srinath Manikandan clarified the timeline. The frequency shift caused by motion of a single quantum of a surface wave, a ripplon, is far below detectable levels currently. But designing lighter and faster mechanical resonators could reach the quantum regime and strongly interact with the system. This isn't just theoretical pride. It's the first step toward testing quantum gravity in a lab. Not in a black hole billions of light years away. Here, on Earth, in a basement in New Jersey. If successful, it bridges quantum mechanics and Einstein's relativity, two frameworks that refuse to talk to each other. Graviton detection forces them into the same room. One experiment, one particle, 90 years of impossible, shattered. Number 2, quantum teleportation through internet cables, December 2024, Northwestern University. Illinois, you send a message through fiber optic cable, classical information, millions of photons carrying your email, your video call, your bank password. Now imagine sending a quantum state through that same cable at the same time. Not a copy. The actual quantum information, teleported, that was considered flatly impossible. Quantum states are fragile. A single stray photon from classical traffic would destroy the quantum information instantly. Like trying to ride a bicycle through a tunnel packed with speeding trucks. You'd be obliterated. December 2024, Prem Kumar's team at Northwestern University did it anyway. They published results in the journal Optica showing successful quantum teleportation over 30 kilometers of fiber optic cable actively carrying internet traffic. Nobody thought it was possible. Kumar's own words: "This is incredibly exciting because nobody thought it was possible. The method exploits wavelength selection and noise management. Classical internet traffic uses certain wavelengths of light. Kumar's team identified specific wavelengths where quantum photons could travel safely. They chose wavelengths carefully to minimize interference. Then they used special filters to reduce noise from classical traffic. The quantum signal travels in a less crowded wavelength band. The two types of communication coexist on the same fiber without destroying each other. It's like finding a quiet frequency on a radio dial jammed with stations. Quantum teleportation works through entanglement. Two particles become linked so their quantum states correlate no matter how far apart they are. Measure one particle, you instantly know the state of the other. But you can't send faster than light messages this way. You still need classical information to complete the teleportation protocol, the quantum state transfers, but not the ability to control what that state is before measurement. What entangled particles do is act as perfect authenticators. If someone tries to intercept the transmission, the quantum states lose correlation. You detect the eavesdropper immediately. Security becomes absolute. The Northwestern experiment used 3 photons, 1 photon to be teleported, 2 entangled photons as the quantum channel. All 3 photons started in the lab. 1 entangled photon traveled through 30 kilometers of fiber carrying regular internet traffic. Classical communications and quantum communications shared infrastructure. The entangled photon survived. Its quantum state remained intact, despite millions of classical photons swarming the cable. When the team performed measurements, the quantum state teleported successfully. Fidelity exceeded classical limits. The experiment confirmed quantum information can coexist with internet traffic. This shatters infrastructure requirements. You don't need separate dedicated quantum networks. Existing fiber optic cables will work. Kumar emphasized the point. If we choose wavelengths properly, we won't have to build new infrastructure. Classical and quantum can coexist. The implication hits hard. Quantum internet becomes vastly cheaper and faster to deploy. No new cables, no new towers. Use what's already underground. The quantum connectivity securely links geographically distant nodes through infrastructure that already exists. Companies and research institutions conducting joint research and finance, drug discovery biotechs. And quantum computing can access quantum channels without waiting decades for specialized networks. Prior quantum teleportation experiments required isolated systems. Researchers at the National Institute of Standards and Technology teleported quantum information over 102 kilometers of spooled fiber in a Colorado laboratory in September 2015. But that fiber carried nothing else. No traffic, no noise, just the quantum signal in perfect isolation. Other teams achieved longer distances through free space. In June 2017, Chinese scientists used the MISSIS satellite to teleport quantum information from Tibet to orbit, distances between 500 and 1,400 kilometers, depending on satellite position. Record-breaking. But satellite-to-ground systems face weather, atmospheric interference, and the enormous cost of launching satellites. Fiber optic cables offer flexibility and reliability that satellites can't match. The Chinese team, led by Guangkan Guo and Cheng Zhou at the University of Electronic Science and Technology, pushed metropolitan quantum teleportation to 7.1 qubits per second in May 2023. Published in Light Science and Applications. A huge rate improvement. They used a single piece of fiber pigtailed, periodically poled lithium neobate waveguide to generate entangled photon pairs. High-quality quantum entangled light source with a 500 MHz repetition rate. The system operated over metropolitan range, with both quantum state tomography and decoy state methods, confirming fidelities well above the classical limit of 66.7%. But even this system didn't share infrastructure with classical traffic. It used dedicated dark fibers belonging to the university backbone network. Only quantum signals traveled those cables. Kumar's team broke that barrier. They proved quantum and classical can share the same physical cable simultaneously. The quantum signal doesn't drown. The filters and wavelength selection protect it. Kumar described the discovery as opening a path toward next-generation quantum and classical networks sharing unified fiber optic infrastructure. The team's success came from quantifying light scattering to find exact areas to place photons, keep them safe from other particles. The approach successfully worked in experiments carrying regular internet traffic. Real-world conditions, no isolation, no protection, just quantum information riding alongside your email. The experiment represents a monumental step toward quantum-connected computing networks, enhanced encryption, and powerful new sensing methods. Quantum teleportation provides quantum connectivity securely between geographically distant nodes. Many people assumed nobody would build specialized infrastructure to send particles of light. Kumar proved them wrong by showing specialized infrastructure isn't needed. Choose wavelengths properly. Classical communications and quantum communications coexist. The physics works. The engineering scales. The infrastructure already exists. 30 kilometers done. The next target is longer distances. More traffic. More quantum channels running through the same cables that stream your movies and carry your texts. Number 3. Fractional excitons and the quantum Hall effect. January 2025, Brown University, Rhode Island. You think particles are either fermions or bosons? Electrons are fermions. Photons are bosons. That's the rule. Matter versus force carriers. 2 categories. Done. Except Brown University physicist Jia Li found particles that refuse both categories. January 8th, 2025. Li's team published results in Nature showing a new class of quantum particles called fractional excitons. These particles don't fit the rules. They carry fractional charge. They show properties of both fermions and bosons. They act like anyones, but with unique characteristics that set them apart even from anyones. They're something else. A third category, nobody predicted. The discovery centers on the fractional quantum Hall effect. Start with the classical Hall effect. Apply a magnetic field to a material with electric current flowing. You create a sideways voltage. Add quantum mechanics. Cool the system to extremely low temperatures. Apply high magnetic fields. The sideways voltage increases in discrete jumps. That's the quantum Hall effect. Push further. The steps become fractional. The voltage increases by fractions of an electron's charge. Not whole numbers, fractions. 1/3, 1/5. Particles carrying fractional charge appear. This is the fractional quantum Hall effect. Li's team built a structure with 2 thin layers of graphene, separated by an insulating crystal of hexagonal boron nitride. Graphene is a 2-dimensional nanomaterial, 1 atom thick. Carbon atoms arranged in a honeycomb lattice. The team sandwiched 2 graphene sheets with insulator between them. They cooled the system to near absolute zero, applied strong magnetic fields, then fired photons at the structure. The photons excited the electrons in the graphene. The electrons formed excitons, bound pairs of an electron and a hole. But these excitons carried fractional charge, not integer charge, fractional. The team measured the excitons using specialized equipment. They observed physical properties consistent with quantum geometry predictions. The excitons showed spin-2 nature, characteristic energy gaps between ground and excited states. Dependence on filling factors relating the number of electrons in the system to the magnetic field, these properties match gravitons. Not coincidence. Fractional excitons and gravitons both result from quantized metric fluctuations. The fabric of space-time randomly pulled and stretched in different directions. In condensed matter systems, electrons interact so strongly that collective excitations mimic behavior predicted for fundamental particles in quantum gravity. The excitons behaved strangely. They showed tendencies of both fermions and bosons. Fermions obey the Pauli exclusion principle. No two identical fermions occupy the same quantum state. Bosons pile into the same state freely. The fractional excitons did both. Almost hybrid, like anyone's, but different. Anyons exist in two-dimensional systems where particle exchange statistics become exotic. Clockwise versus counterclockwise, paths around another particle produce different phase factors. The fractional excitons exhibited unique properties that set them apart from known anyons. Naiyuan Zhang, PhD student and co-first author, stated the unexpected behavior suggests fractional excitons could represent an entirely new class of particles with unique quantum properties. Lai described the significance. This is the first time we've shown that these types of particles exist experimentally. Now we're delving deeper into what might come from them. The team used samples prepared by longtime collaborators at Princeton University. Postdoctoral researcher Lingjie Du spent over 3 years building low-temperature optical equipment in his new lab in China. The measurements were completed at Columbia University by physicist Corey Dean and the team. They observed fractional excitons in a fractional quantum Hall effect liquid. These liquids are systems of strongly interacting electrons occurring in 2 dimensions at high magnetic fields and low temperatures. They can be theoretically described using quantum geometry, emerging mathematical concepts applying to minute physical distances where quantum mechanics influences physical phenomena. The discovery came from a technique called low-temperature resonant inelastic scattering, pioneered by the late Aaron Pinchuk, Columbia physicist who passed before seeing the final results. The method measures how photons scatter when they hit a material, revealing the material's underlying properties. Pinchuk's approach allows probing collective excitations in quantum systems, modes with spin that emerge from electron interactions. The team measured these modes for the first time in the fractional quantum Hall regime. Pinchuk would be very proud, said his colleague. The experiment marks the first substantiation of the graviton concept posited by pioneering works in quantum gravity since the 1930s. Now realized in condensed matter, Lingjie Du, former Columbia postdoc and senior author, emphasized the milestone. The fractional excitons persist for measurable times. Their properties are stable enough to study, but they require extreme conditions, temperatures near absolute zero, magnetic fields measured in teslas, clean samples with minimal defects. The physics demands precision. One contaminated atom destroys the effect. 1 degree too warm and the quantum correlations vanish. The team's next steps involve studying how fractional excitons interact. Can their behavior be controlled? Can they be used for quantum information processing? The questions multiply. This feels like we have our finger right on the knob of quantum mechanics, said physicist Dima Feldman, professor at Brown and co-author. It's an aspect of quantum mechanics we didn't know about or didn't appreciate before now. Number 4. Superconducting quantum computers breaking error thresholds, December 2024. Google Quantum AI, California. Quantum computers fail constantly. Noise destroys qubits. Errors cascade. Calculations collapse. Every quantum computer faces this. More qubits means more noise, means more errors, means useless output. For 30 years since Peter Shor proposed quantum error correction in 1995, the field chased one goal: go below threshold. Scale up qubits while driving errors down exponentially. Show that adding more qubits reduces error rate instead of increasing it. Nobody achieved it. Until December 9th, 2024, Google Quantum AI announced Willow, a 105 qubit superconducting processor that crossed the threshold. The team tested ever larger arrays of physical qubits, grid of 3x3 encoded qubits, then 5x5, then 7x7. Each time they scaled up, they cut the error rate in half. Exponential reduction, below threshold. The Holy Grail. Hartmut Neven, lead scientist, called it a historic accomplishment. Willow can reduce errors exponentially as it scales using more qubits. That's the breakthrough. More qubits equals fewer errors. Counterintuitive but proven. The chip performed a benchmark computation in under 5 minutes that would take one of today's fastest supercomputers, 10 to the 25th years. 10 septillion years. Longer than the age of the universe by a factor of a billion. The benchmark is called random circuit sampling. Classically hardest task a quantum computer can do today, entry point for quantum computing. If you can't beat classical computers on random circuit sampling, there's strong reason for skepticism you can tackle more complex quantum tasks. Google used this benchmark to track progress from generation to generation. Sycamore results in October 2019, updated results in October 2024. Now Willow crushes both. The performance is astonishing. 5 minutes versus 10 septillion years. The gap is absurd. Willow was fabricated in Google's new state-of-the-art facility in Santa Barbara, one of only a few facilities in the world built from the ground up for superconducting qubit fabrication. System engineering drives everything. All components must function simultaneously at high performance. Single qubit gates, 2 qubit gates, qubit reset, readout. If any component lags or 2 components don't function well together, system performance drags down. Maximizing performance informs all aspects: chip architecture, fabrication, gate development, calibration, quality over quantity. Producing larger numbers of qubits doesn't help if they're not high enough quality. The chip delivers best-in-class performance at scale. Across the entire 105 qubit array, single qubit gate fidelities hit 99.97%. Entangling gates 99.88%. Readout 99.5%, all operating at unmatched speed, tens to hundreds of nanoseconds. These high-precision quantum gates enabled the team to perform highly complex algorithms involving large-scale quantum interference and entanglement, placed results in a regime beyond classical computer capabilities. The precision matched with speed. The system performs millions of measurements in tens of seconds. Over the course of the project, the team executed 1 trillion measurements. A significant portion of all measurements ever performed on all quantum computers combined. Independently, Harvard University physicist Mikhail Lukin and colleagues at MIT and Quira Computing demonstrated quantum error correction on an atomic processor with 48 logical qubits. Published results showed a different architecture achieving similar error correction milestones. Lukin's team used neutral atom qubits. Google used superconducting circuits. Both proved below-threshold error correction works. Physics World named both achievements co-winners of the 2024 Breakthrough of the Year in December 2024. Editor-in-Chief Matan Durrani explained the significance. The 2 winners have done very complementary experimental work in quantum error correction. This moves us closer to a day when quantum computers become practical problem-solving machines, not just noisy intermediate-scale tools for scientific research. China matched Google's scale with Zhuchangxi 3.0. Jian Weipan's team at the University of Science and Technology of China demonstrated their own 105-qubit superconducting processor in March 2025, published in Physical Review Letters. The device achieved world-leading fidelity metrics. Single qubit gate 99.9%, 2 qubit gate 99.62%, readout 99.13%. One journal reviewer called it benchmarking a new superconducting quantum computer with state-of-the-art performance. Zhuchangxi 3.0's architecture integrates frequency-tunable qubits, topological coupling, and flip-chip bonding. Decoherence performance surpasses Sycamore. Quantum coherence time measures how long a quantum system retains operational integrity. Longer time enables execution of complex algorithms and large-scale computations. The Chinese team's advance pushed the field forward neck and neck with Google. Fujitsu and Riken announced a 256-qubit superconducting quantum computer in April of 2025. 4 times larger than their 2023 system. Plans for a 1,000-qubit machine by 2026. IBM outlined a fault-tolerant roadmap targeting Starling by 2029. 200 logical qubits running 100 million error-corrected operations. Microsoft introduced Majorana 1, a topological qubit architecture aiming to scale to millions of qubits using new superconducting materials. The race accelerates. Every few months, a new record. More qubits, lower errors, faster gates. The milestones pile up. These aren't lab curiosities. Google explored using Willow's processor to study quantum scrambling. Sheds light on properties of black holes. Provides clues about quantum gravity. IBM's Starling will house in a new quantum data center in New York. Introduces quantum low-density parity check codes, slashing overhead by 90%. Outlines future systems like BlueJay with 1,000 plus logical qubits executing 1 billion operations. Practical modular fault-tolerant machines. The era of useful quantum computing approaches. Superconducting qubits lead the pack. 40 years of research from John Clark, Michel Devoret, and John Martinez, earning them Nobel laureate status in 2025. The platform balances performance and scalability. Mature integrated circuit fabrication and active research in academia and industry prove the approach works. Number 5. Time crystals connected to reality. October 2025, Aalto University, Finland. Time crystals shouldn't exist. Perpetual motion violates thermodynamics. Energy dissipates. Motion stops, always, except in the quantum realm where rules bend. Nobel laureate Frank Wilczek proposed time crystals in 2012. A system whose lowest energy state moves in perpetual rhythm, forever oscillating without consuming energy or winding down, particles arranged periodically in time instead of space, like a pendulum swinging forever without friction. Not because it defies gravity, because it never loses energy. Quantum miracle. First experimental time crystals were confirmed in 2017, but they lived in isolation. Disturb them and their delicate motion collapsed. Connect them to anything external and they died instantly. That was the rule. October 16th, 2025, Jerry Makinen's team at Aalto University broke the rule. Published in Nature Communications, they coupled a time crystal to an external mechanical system while maintaining perpetual oscillations. First time ever. Changes everything. The experiment took place in Aalto's low-temperature laboratory, part of Otonano, Finland's national research infrastructure for nano, Waki, micro, and quantum technologies. The researchers used radio waves to pump magnons into superfluid helium-3 cooled to near absolute zero. Magnons are quasi-particles, groups of particles behaving as individual particles, collective magnetic excitations. When the team turned off the pump, the magnons formed a time crystal, stayed in motion for 108 cycles, several minutes. Before fading to levels, the researchers could no longer observe. During the fading process, the time crystal connected itself to a nearby mechanical oscillator, a tiny vibrating system whose motion could be precisely measured. The connection wasn't random. It depended on the oscillator's frequency and amplitude. The crystal responded to the rhythm of its partner. The two systems synchronized. Behaviors intertwined in a dance of quantum mechanics and classical physics. Makinen explained the interaction mirrors optomechanical phenomena. Same physics allowing LIGO to detect faint ripples in spacetime from colliding black holes. Both systems rely on detecting incredibly subtle shifts in frequency and energy. Perpetual motion is possible in the quantum realm so long as it's not disturbed by external energy input. Observing it counts as disturbance. That's why time crystals had never been connected to external systems, but Makinen's team did it. They showed you can adjust the crystal's properties using this method. The coupling confirmed nonlinear interaction between the time crystal and surface waves in superfluid helium-3. The interaction mimics dynamics of optomechanical systems used in precision physics. Findings suggest time crystals could enhance quantum technologies, serve as long-lived memory elements, frequency references in quantum computers and sensing devices. Time crystals last for orders of magnitude longer than quantum systems currently used in quantum computing. Best case scenario is time crystals could power memory systems of quantum computers to significantly improve them. They could also be used as frequency combs, employed in extremely high sensitivity measurement devices as frequency references. The current coupling strength is weak. Frequency shift caused by motion of a single quantum of the surface wave, a ripplon, is far below detectable levels. Back reaction. From the time crystal on surface motion is negligible. True bidirectional control has yet to be achieved. Despite limits, the experiment demonstrated exquisite sensitivity, operating in one of the coldest liquids ever studied. Even tiny dissipations were measurable through temperature changes recorded using the time crystal itself as a thermometer. Next frontier involves designing lighter and faster mechanical resonators. Perhaps nanomechanical beams or membranes can reach quantum regime and strongly interact with magnetic time crystals. Replacing large liquid surface with nanoscale resonators could dramatically enhance coupling strength. Lighter resonators vibrate at much higher frequencies, achieve quality factors, orders of magnitude, greater than liquid waves. Brings the system closer to quantum limit, could make it possible to control or entangle mechanical and time crystal states. Other labs pushed time crystal research forward. Vienna University of Technology demonstrated in October 2025, published in Physical Review Letters, that quantum correlations can stabilize time crystals. Contrary to previous assumptions, quantum fluctuations enhance rather than hinder formation. Using laser trap lattice, the team demonstrated self-organizing rhythmic behavior arising purely from particle interactions. Zhejiang University and Tsinghua. University implemented topologically ordered time crystal on quantum processor for first time. published in Nature Communications, November 2024. 18. Programmable superconducting transmon qubits arranged in two-dimensional square lattice. Surface code supporting exotic topologically ordered phases. Time translation symmetry breaking combined with topological order adds stability and robustness. Requirement for quantum computing applications. University of Chinese Academy of Sciences, researchers used discrete time crystal to enhance stability of quantum states in quantum computer in February 2024. Potentially first practical use of time crystal. Team led by Biao Huang stabilized Greenberger-Horn-Zeilinger states. Complex quantum state representing large-scale entanglement of qubits. By employing discrete time crystal as control mechanism, Team constructed SafeHouse to protect the GHZ state. Achieved less fragile configuration of 36 qubits compared to previously unstable, larger state that included up to 60 qubits. Application of microwave pulses to qubits induced quantum properties to oscillate and form time crystal. Minimized disturbances that typically disrupt GHZ state. Time crystals challenge foundation of thermodynamics. Invite new ways of thinking about matter and information. From Alto's frozen laboratories to quantum startups and global tech giants, interest in hybrid quantum systems accelerates. Next leap may come from turning elegant experiments into functional devices, powering quantum revolution already unfolding. Perpetual motion is here. It's quantum. It's real. It's connected to the world we live in. Number 6. Quantum teleportation distance records. July 2017 to December 2024. Space and fiber, 1,300 kilometers, ground to satellite. Chinese scientists using the Mauritius satellite teleported quantum information from Tibet to orbit in July 2017. Distance exceeded every prior record by an order of magnitude. The team fired a laser beam carrying an entangled photon from a ground station to the satellite. They entangled the photon on the ground with a third photon, measured their quantum states. The photon on the ground had its quantum state teleported to orbit. Information traveled without the particle traveling. Quantum state transferred instantaneously, limited only by speed of light for classical confirmation signal. The Chinese team, led by Jigang Ren at the University of Science and Technology in Shanghai, published results showing entanglement worked over distances from 500 to 1,400 kilometers, depending on satellite position in orbit. Mauritius is a low Earth orbit satellite, first quantum communication satellite, launched August 2016, demonstrated quantum entanglement distribution, quantum key distribution, and quantum teleportation from space to ground. Efficiency of transmission over prior fiber optic experiments increased by order of magnitude. Space offers no atmospheric scattering over long distances. Vacuum preserves quantum states better than fiber or open air. But space requires satellites. Satellites cost billions. Satellites face weather delays. Ground-based systems offer flexibility satellites cannot match. European Space Agency set previous record in 2012 using optical ground station in Canary Islands. Researchers from Austria, Canada, Germany, and Norway transferred physical properties of one photon to its entangled partner across 143 kilometers between La Palma and Tenerife, both islands in the Canaries off coast of Spain. All 3 photons started on La Palma. One entangled photon was sent through air 89 miles to Tenerife. Since particles were entangled, measurement of quantum states of 2 particles on La Palma affected particle on Tenerife. First particle essentially recreated a new location without traversing distance. Austrian Academy of Sciences physicist Rupert Urson commented, "Next step would be achieving quantum teleportation to satellite in orbit to demonstrate quantum communication on global scale." National Institute of Standards and Technology in Colorado set fiber optic record in September 2015. Researchers teleported quantum information over 102 kilometers of spooled fiber. Transfer of quantum information contained in one photon, its specific time slot in a sequence, to another photon transmitted over fiber. Lead author Hiroki Takesui was NIST guest researcher from NTT Corp in Japan. Achievement made possible by advanced single-photon detectors designed and made at NIST. Only about 1% of photons make it through 100 kilometers of fiber. NIST physicist Marty Stevens stated, "We never could have done this experiment without these new detectors, which can measure this incredibly weak signal." May 2023, Chinese team at University of Electronic Science and Technology improved metropolitan quantum teleportation rate to 7.1 qubits per second. Published in Light Science and Applications. Used single piece of fiber pigtailed periodically poled lithium niobate waveguide to generate entangled photon pairs. High quality quantum entangled light source with 500 MHz repetition rate. Team employed quantum state tomography and decoy state methods to calculate teleportation fidelities, well above classical limit of 66.7%, high-speed metropolitan quantum teleportation achieved. The system presents new record for quantum teleportation over metropolitan range, April 2025. University of Illinois, Urbana-Champaign achieved quantum teleportation with 94% fidelity using nanophotonic indium gallium phosphide platform to perform nonlinear sum frequency generation. December 2024. Northwestern University demonstrated quantum teleportation over 30 kilometers of fiber optic cable, simultaneously carrying regular telecommunications traffic. Eliminated need for separate dedicated infrastructure. Showed quantum teleportation and classical communications can coexist on same fiber optic cables. Less crowded wavelength of light used for quantum signal. Special filters required to reduce noise from other traffic. Prem Kumar. Northwestern computing engineer who led study, stated this is incredibly exciting because nobody thought it was possible. The progression shows acceleration. 100 kilometers in fiber in 2015, 143 kilometers in open air in 2012, 1,300 kilometers space to ground in 2017, metropolitan speeds hitting Hertz rates in 2023. Coexistence with internet traffic in 2024. Each advance unlocks new capabilities. Secure quantum key distribution for unbreakable encryption. Quantum internet linking quantum computers across continents. Distributed quantum sensing networks. The infrastructure builds piece by piece. Distance records fall. Fidelity improves. Integration with existing systems succeeds. The quantum network approaches reality. Number 7. Quantum simulation of molecular chemistry. May 2025. University of Sydney, Australia. Simulating chemistry is hell. Molecules have electrons. Electrons interact. Interactions grow exponentially with system size. A molecule with 50 electrons requires computational resources beyond every classical computer on Earth. Combined, standard quantum chemistry methods break down. You can't simulate complex molecules accurately. Can't predict how they behave when light hits them. Can't model ultra-fast chemical processes that underpin photosynthesis, DNA damage, or drug interactions. The wall is hard. Classical computing hits it and stops. Quantum computers promise to break through. They operate using quantum mechanics natively. Molecules are quantum systems. Simulating quantum systems with quantum computers should be natural, except it wasn't. Until May 15th, 2025. University of Sydney quantum chemist Ivan Casal and Physics Horizon fellow Tingray Tan published results in Journal of the American Chemical Society showing first quantum simulation of chemical dynamics with real molecules, not static properties. Dynamics, time-evolving processes, how molecules behave when excited by light, full interaction between light and chemical bonds, position and energy of the molecular system at any time point. Like understanding a mountain hiker's journey through mountains, not just start and end points. The team used trapped ion quantum computer and University of Sydney Nanoscience Hub, employed highly resource-efficient encoding scheme using both qubits and bosonic degrees of freedom, analog quantum simulation method using single trapped ion, fraction of hardware resources needed by traditional digital quantum computers. Performing same simulation using conventional approach in quantum computing would require 11 perfect qubits and 300,000 flawless entangling gates. Their approach is about 1 million times more resource efficient. Enables complex chemical dynamics to be studied with far fewer resources than previously thought possible. The simulations captured light-driven chemical changes, non-adiabatic chemical processes, among most difficult problems in computational chemistry because they involve strong coupling between electronic and nuclear motions. When molecules absorb light, electrons jump to excited states. Nuclei start moving. Electronic and vibrational changes happen ultra-fast, femtoseconds to picoseconds. Classical computers struggle to model this accurately or efficiently. The quantum computer handled it, simulated dynamics of 3 different molecules, demonstrated programmability and versatility, also simulated open system dynamics in condensed phase, all with same quantum resources. Applications range wide: photosynthesis, DNA damage caused by UV radiation, advanced medical therapies like photodynamic therapy for cancers or skin disorders, sunscreens, energy conversion and storage systems, battery chemistry, drug design. Anywhere light interacts with molecules, this matters. Castle stated, this experimental breakthrough demonstrates quantum simulation of real complex molecules is within practical reach. Achievement could dramatically accelerate scientific discovery in chemistry and beyond. Harnessing power of quantum mechanics in highly resource-efficient way opens promising new pathway. Quantinuum announced world's first scalable error-corrected end-to-end computational chemistry workflow in 2025. First practical combination of quantum phase estimation with logical qubits for molecular energy calculations. Essential step toward fault-tolerant quantum simulations. Demonstrated on H2 quantum computer using state-of-the-art chemistry platform in Quanto. Proving quantum error-corrected chemistry simulations are not only feasible but scalable and implementable in quantum computing stack. Team investigated 2 state preparation methods. First uses Givens rotations to save computational costs. Second exploits sparsity of molecular wave function to maximize efficiency. Results showed sparse state preparation scheme performed especially well. Required fewer gates and shorter runtimes than alternative methods. Google's Sycamore quantum processor performed largest chemistry simulations involving quantum computers in November 2022, reported by IEEE Spectrum. Employed up to 16 qubits on 53-qubit quantum computer to calculate ground state of molecules, simulated H4-Urbx, molecular nitrogen, and solid diamond, involved as many as 120 orbitals. Hybrid approach combined classical and quantum computation. Classical computer handled most of fermionic quantum Monte Carlo simulation. Quantum computer stepped in during last most computationally complex step, calculating differences between estimates of ground state made by quantum computer and classical computer. Harvard University published theoretical framework for simulating strongly correlated quantum systems in chemistry using Rydberg atom arrays in December 2023, reported in Nature Physics January 2025. Multi-institution team offered flexible quantum toolbox for simulating time evolution of spin Hamiltonians. Used mix of computational approaches and engineering methods, including hardware-specific multi-qubit gates for Rydberg atom arrays. Showed how to optimize hardware operations to accurately realize complex spin-spin interactions. Introduced algorithm for extracting chemically relevant spectral properties via classical coprocessing of quantum measurement results. Enabled evaluation of excitation energies and finite temperature susceptibilities from single dataset. IonQ and ANSYS ran medical device simulation on IonQ's 36-qubit computer in March 2025. Achieved approximately 12% speed up over classical high-performance computing. One of first cases showing practical quantum outperforming classical method, AstraZeneca collaborated with Amazon Web Services, IonQ, and NVIDIA to demonstrate quantum-accelerated computational chemistry workflow for chemical reaction used in synthesis of small molecule drugs in June 2025. Boehringer Ingelheim collaborated with PsiQuantum to explore methods for calculating electronic structures of metalloenzymes critical for drug metabolism in January 2025. McKinsey estimated quantum computing's potential value creation in life sciences at $200 billion to $500 billion by 2035. Source of value is quantum computing's unique ability to perform first principles calculations based on quantum mechanics, not approximations, not classical shortcuts. Direct simulation of quantum-level interactions, critical for drug development. Precision in protein simulation. Enhanced electronic structure simulations. Improved docking and structure-activity relationship analysis. Prediction of off-target effects. Creating more precise simulations of reverse docking helps identify potential side effects and toxicity early in development. Reduces risk of failures later in process. Chemistry simulation on quantum computers moves from theoretical promise to experimental demonstration. From static energy calculations to full dynamics. From small test molecules to pharmaceutically relevant systems, the machines work. The algorithms improve. The applications multiply. 1 million times more efficient than prior approaches. Accurate simulation of light-driven processes that classical computers cannot handle. Real molecules, real chemistry, real quantum advantage. In your lifetime, 7 experiments, graviton detection using quantum sensors and Weber bars at Stevens Institute, quantum teleportation through active internet cables at Northwestern, fractional excitons in quantum Hall systems at Brown, superconducting quantum computers crossing error correction thresholds at Google and Harvard, time crystals coupled to external systems at Alto. Quantum teleportation over 1,300 kilometers space to ground using MICHUS. Molecular chemistry simulations 1 million times more efficient at University of Sydney. Each one operates at extremes, temperatures near absolute zero. Magnetic fields measured in Teslas, particles lasting femtoseconds, distances spanning continents, fidelities exceeding 99%, error rates dropping exponentially, resources scaling to millions of qubits. These aren't proposals. They're running, right now. Labs in California, Massachusetts, Rhode Island, New Jersey, Illinois, Finland, China, Australia. published in Nature, Physical Review Letters, Nature Communications, Optica, Journal of the American Chemical Society. Dates ranging from August 2024 through October 2025. Sources cited include Stevens Institute research accessed 34,000 times in 2024. Vienna University of Technology's Physical Review Letters paper from October 2025, tracking time crystal quantum correlations. Northwestern's December 2024 Optica publication on quantum teleportation through internet infrastructure. Brown University's January 2025 Nature paper on fractional excitons. Google's December 2024 announcement of Willow achieving below threshold error correction. Aalto University's October 2025 Nature Communications paper showing first-time crystal coupled to external system. And University of Sydney's May 2025 Journal of the American Chemical Society paper demonstrating million times more efficient molecular dynamics simulation. The experiments converge. Quantum error correction enables large-scale quantum computers. Quantum computers simulate chemistry accurately. Chemistry simulation designs new drugs and materials. Quantum networks link computers securely. Quantum sensors detect gravitons. Graviton detection tests quantum gravity. Quantum gravity unifies physics. Time crystals power quantum memory. Memory enables fault-tolerant computation. Computation solves problems. Classical machines never will. The pieces connect. The revolution builds. In basements and clean rooms and laboratories cooled to millikelvin, with superconducting circuits and trapped ions and Rydberg atoms and graphene sheets and helium-3 superfluids, you're watching it happen. Not in science fiction, not in theory, in practice, in papers published this year, in machines you can access through cloud services, in experiments that graduate students run before breakfast. The most intense quantum experiments in history operate today. They challenge reality. They detect the impossible. They teleport information. They simulate molecules. They break symmetries in time itself. They push physics to limits that sound absurd. Temperatures 1,000th of a degree above absolute zero. Fidelities above 99.9%. Coherence. Times lasting minutes. Entanglement over thousands of kilometers. Error correction below threshold. Chemistry simulation 1 million times more efficient. Graviton detection within experimental reach. 7 experiments, 7 frontiers, 1 lifetime. Yours. This is quantum physics in 2025. Intense, real, running, now.